Hi everyone, I'm Eric Tao. This is one of a series of videos in the Reimagining Precalculus project. And our goals here are to give you a brief and accessible introduction to key course concepts and then tie those to an application. For this video, we really have three objectives, and they're all related to graphing in one way or another. So in the beginning for this video, we're looking at polynomial functions. We would like to graph a polynomial function from the zeros, analyze behavior near the zeros, and use test points. Secondly, we'd like to do the same thing with rational functions, and that'll include asymptote information along with test points. And then thirdly, being able to use this in general, this information, we call it the key information, and test points to sketch a graph of a function. Before we begin, let's think just a moment about how calculators can graph functions for us, and then we'll compare that to how humans, how people can sketch graphs and accomplish that same task as a calculator might. So first, how does a calculator graph a function? If you have a graphing calculator, you know how you can type in a function and you go right to the graph and it generates itself on the screen. So what's really happening there is the calculator takes thousands of points, thousands of x values, it substitutes those, evaluates them in the function, that gives us y coordinates, and so we have thousands of points in two-dimensional space, x and y coordinates together, and it plots them all together. And by the end of that, there's so many points that you can't really distinguish as it being a scatter of points or a smooth connected curve. So this is how calculators are able to give us these really nice graphs. Let's contrast that with how a person might sketch the graph of a function. We can't plot thousands of points. It's not practical. So typically what people do is we pick a handful of points, maybe 5 or 6. And we have those in the graph. And then once we have some idea of what the curve shape is, we're able to connect those points together with some type of smooth connected curve. So the trick here is to know which points to pick. We'd like to pick the points well, not just randomly. And this is what key points are. This is what test points are. They're a way of choosing those points well so that you can get a graph sketched by hand without having to pick thousands and thousands of points. Before we look at the full graphing techniques for this video, let's consider the behavior of a couple of types of underlying function. And the first type we'll consider are power functions. And you can see some of these on the left. These are functions that are just a power of x. So the ones that are being displayed right now, that's y equal x, x cubed, x to the 5th, and x to the 7th power. All of those have the property that the power of x is odd. And in this case, if we have an odd power function, all of those should rise as they move to the right and fall as they move to the left. We can see for y equal x that it's just a diagonal line, but it is rising to the right, it's falling to the left. The other three are more of an S curve. They flatten out in the middle, but they still have that property. As you go off to the right from 0, you'll see it rising upward, and then as you move to the left, it's falling downward. Now, those are the odd power functions. If we consider the even power functions, I'll throw them on the same screen as the odd ones. So we can see in red, the even power functions have a very different behavior. In this case, they're rising to the right and the left. We have a U-shaped curve instead of an S-shaped curve. And I'll take away the odd power functions so we can see them more clearly. The ones that I've got on the screen are x squared, x to the 4th, x to the 6th, x to the 8th. X squared is a parabola. We can see that upward opening U-shaped curve for the parabola. But the other three are also some variation on a U-shape. They're all opening upward. And so we say here that these functions will rise to the right and rise to the left. And so what we've got here between the odd and the even power functions are different kinds of end behavior. And remember, all end behavior means is what the y-coordinate of the function is doing as you move to the right and the left edges of the graph. So we can see for odd power functions, those will rise to the right and fall to the left. For even power functions, they will rise to the right and the left. Let's consider the other type of function that might show up with graphs, and these could show up with graphs of rational functions. These are what I call reciprocal functions. And a reciprocal function is 1 over a power of x. And you can see here I've got 4 of them graphed on the right side. If you follow the equations on the left, we have y equal to 1 over x, 1 over x cubed, 1 over x to the 5th, and 1 over x to the 7th. And those are all odd powers of x. And we can see there's a vertical asymptote in the middle. So when x is 0, all of those functions are undefined. We can't divide by 0. But as we look to that vertical asymptote, we can see what's happening to the function. So if we're approaching that vertical line in the middle from the left, the function is falling. And we say here that it falls to negative infinity. It's heading toward the bottom of the graph. As x approaches the vertical asymptote from the right, so as we're coming over on that right-hand branch, we can see that they're all moving upward. So we would say here that as we approach the vertical asymptote from the right, the function will rise, in this case, to positive infinity. As you might expect at this point, there is a different type of behavior for the even reciprocal functions. And looking at all the reciprocal functions together, you can see those even ones in red moving up. And this is the difference in behavior between the two. So for the ones that I've selected here, I've got 1 over x squared, 1 over x to the 4th, 1 over x to the 6th, and 1 over x to the 8th. With all those even powers, we look at the same asymptote, but now we see that as you come in from the left or the right, it will be rising to infinity. So we have, for both of those functions, different kinds of asymptote behavior. So for that vertical asymptote, you can either rise or fall. For the odd ones, we fall to negative infinity as we come in from the left, but we rise as coming in from the right. And then for the even reciprocal functions, it rises as you approach that vertical asymptote from either direction. For our first example, we'll look at a polynomial function, and you can see it here. We have f of x in factored form, so we don't have any factorizations to do up front. This one is negative 1/4 times x squared times the quantity x plus 3, and then times the quantity x minus 4. Now, if a polynomial function is given to you in a non-factored form, you would in principle need to find the factorization. Our goal here isn't necessarily to factor it, but to interpret the factorization and understand how that affects the graph. The very first thing we need to do here is consider the end behavior of the function. So that's the behavior of the graph as you go far off to the right or the left side. We sometimes say as x goes to infinity to the right or minus infinity to the left. And the trick here is to look at the leading terms. And remember, by a leading term in a polynomial, I mean the highest power of x that we see. And since it's in factored form, we can take each factor individually and look at the leading terms from each one. And I'll show you how that works in this particular case. So if there are parentheses, it's easy to tell what the factor is. And if I look at my x plus 3 factor in the middle, the highest power of x is the x itself. We think of that as x to the 1 power. So my leading term, I'll just mark the x in that case. And then likewise with the other factor, the x minus 4 in parentheses, I mark the x there as the leading term. So I've got 2 of them marked out. And then for the initial term, it's not obvious what the factor is, but let me add some parentheses here. We can take the minus 1/4 x squared all together. So that entire thing can be thought of as one term, one factor. And there's only one term, so the leading term is the entire thing. So we'll take all of this together. So there's that power of x, but also the coefficient of negative 1/4 in front. And if we take all those together and ignore everything else, and in this case that means ignoring the plus 3, ignoring the minus 4, we just write out what's left. So I'll do that underneath. We have our minus 1/4 x squared. I have an x, and I'm ignoring the plus 3, and then another x, ignoring the minus 4. And you can tell by getting rid of all those other terms, we have just x's left with a coefficient in front. So simplify, and we get minus 1/4. We have an x squared times an x times an x. So that's an x to the 4th. And that's a power function. So as we've seen, power functions where you have an even power of x, those open in the same direction on either the left and the right. I'll do a little sketch here of what this one would look like. So normally x to the 4th, it would be opening up in both directions. But I do have a negative in front. So that flips it over the x-axis. We have it opening in the negative direction instead. So the graph would look like a U-shaped curve opening downward. And so this is how we determine the end behavior. And the rule here says once you've ignored all the other terms and you've looked only at the leading terms, you get a power function. We know what power functions look like. In this case, it opens downward on both the left and the right. And what we conclude here is that the function f of x will have the same end behavior. So let's sum up what we've done here. We're interested in the end behavior of f of x. And one way we can say this is that as we go to the right, the curve will fall down toward negative infinity. So we can just say falls to the right. And then as we go to the left, it's the same. And we know that because of the even power on x. And we know it's falling because of the negative that was in front of it. So in both directions, this will fall downward. Once we know the end behavior, we can go on and consider what's called the zero behavior. And what you might remember from our earlier video on polynomial and quadratic functions is the zero product property. So if we're interested in when this function is 0, we need to look at each factor separately and figure out which value of x will make it equal to 0. And if you do that here, we get these 3. So we get a negative 3 from the middle factor for x equals 0 from the left-hand factor, and then x equal 4 for the factor on the right. So assuming that you've found all the zeros of your function, and in factored form, that's not too hard to do, we're interested in what the behavior of the curve is, what the graph looks like, near all 3 of those values. And so we'll consider all 3 in sequence. And the idea here is twofold. So first, we need to factor out the factor. And that sounds a little strange, but we have 3 factors here. We'll pull out one at a time and consider what's left. So when you look at the rest of it, we will then plug the x value into that remaining portion. And I'll start with x equals 0 because it'll be easier to see how that happens. And in this case, if x equals 0, we look at our function, we see, oh, the first factor is the one that makes this a 0 of the function. So we'll consider that one on its own. Imagine we've factored it out. And I'll write the factor in front. I'll keep it in parentheses so it's clear. There's our minus 1/4 x squared factor. And then consider the rest of it on its own. And I'll separate it out. So we have the x plus 3, and we have the x minus 4. Now, we know that if x is really equal to 0, the first factor is 0, which makes the entire expression 0. That's the zero product property. What we're doing here is we're taking this portion that I marked out in square brackets, and we're saying, well, what if x equals 0 just for that part? So once we've separated out the factor that makes the entire thing 0, we can make x equals 0 in the rest of it. And this is the trick. So once we've factored out the factor, in this case minus 1/4 x squared, we consider the rest of it, which is the two factors, x plus 3 times the factor x minus 4. We plug the value of 0 into it. And let's see what happens here. So underneath, I have my original factor, minus 1/4 x squared. We leave that alone. We do the other part with x equals 0. And there's not a lot to calculate here. The first factor would be positive 3. The second factor would be a negative 4. And here we have it. Now, we can simplify. And when we do that, we'll see the negative 4 and the negative 1/4 cancel out exactly. So all that's left in this case is 3 and x squared. So I'll put that on the bottom. Now let's think about what that tells us. We've done this little trick to factor out and then plug in the value of x to the rest of it. We get a power function. And what this tells us is that the function f of x, it's going to behave a lot like 3x squared as long as you're close to this x equals 0 value. So we would say f of x behaves like the equation y equal 3x squared as long as we're near x equals 0. And this goes back to what we've already discussed for power functions. So we know what power functions look like. We know which direction they open, either up or down, and whether they're rising or falling to the left or the right. So in this case, we have a 3x squared. That's an even power of x. We know that'll rise to both the right and the left. It'll be a U-shaped curve opening up. And the 3 in front doesn't change that fact. It's not negative, so it'll continue opening upward. So the same behavior will be true for the function f of x when we're near 0. So we can expect some sort of U-shaped curve opening upward. And of course, this function, just like the original one, has a 0 when x is 0. It passes right along the x-axis at that point. So you can see here that the 0 behavior of the function really comes down to determining the power function that you're comparing it to. Once we know that, we know how power functions work, we can do the same comparison there. Now that you've seen how to work through one 0 behavior, this is the one at x equals 0 that I just did, I want you to try the next two. So we have x equal to negative 3, that's a negative here, and then x equal to 4. So I've done the same thing for part 1 for each of these. So I factored out the factor. When x is negative 3, we're interested in the factor x plus 3, so that came out in front with the rest of it on the right in square brackets. And then for x equal 4, I've done the same, the x minus 4 factor in front with the rest of it in square brackets. So what I'd like you to try now is the second part. So plug the x value in each case into that remaining part in square brackets, and you should get a power function. Once you have the power function, think about how that will look as a graph. In my case, at the beginning, I had a quadratic. I had an x squared, so I knew I had a U-shaped curve, and in this case, opening upward. In the other cases, you'll get something different, but if you can sketch a graph of both of the functions you get, you'll have a very good idea of what the function f of x will look like. So take a minute, try it out, and then we'll move on to the next step. All right, let's look over the results of this and make sure that we're understanding the interpretation. Once we're finished here, we'll move on to the graph of the function itself. We have nearly enough information to really get that together. For now, though, we have our two zeros at x equal negative 3 and x equal 4. And if you've gone through all the steps to plug in the value of x, you should have a 15.75 as the number that comes out. Our factor of x plus 3 stays there. And then for x equal 4, we should have a negative 28 in front of the factor x minus 4. Now, the trickier part here is understanding the interpretation of it. So we can go through the mechanics and get the number in front and we have the factor after. But what does it mean? Well, you can see a sketch to the right of each of those. If we look at our 15.75 times x plus 3, that's a line equation. When x is equal to -3, that line is 0. And we know that the behavior of the line is going to be similar to the behavior of the function when we're close to that point. So as x is near -3, f of x and that line will look pretty similar. And it's a positive slope. We have a positive 15.75. So we know that this curve goes upward as you move to the right, and it passes through the x-axis at -3. For the other one, it's a negative number in front, so here -28. We have the line moving downward through that point. But in both cases, we know that those lines will approximate the behavior of the function as long as we're close to the 0 in question. So either -3, we're moving up to the right, or +4, we're moving down to the right. Now let's take everything we've done with our polynomial function and see how we can use that information to sketch a graph. And you can see here on the screen that I've put together our 3 key points. These are the zeros of the function. So we know that at -3, 0, and 4, the function has a y-coordinate of 0. Those are also plotted over on the right-hand side on the graph. In addition to those key points, we know some things about the 0 behavior. So as the function passes through those 3 zeros, it has different types of behavior. I'll open this up and we can see the 3 functions we found. And we used our technique of factoring out one of the factors and then plugging in or evaluating the rest of it for the given value of x. And if I switch those on, we can see the 3 small sketches that we did on the board showing up on the graph. So for -3 and 4, we know the function behaves like a line. That was what we came out with. We had 15.75 times the quantity x plus 3 as one of our equations. And then the other one was -28 times x minus 4. So for the 0 at -3, that's an upward moving curve, rising to the right, falling to the left. Then for 4, it was rising to the left, falling to the right. For x equals 0, that one ended up looking like a parabola, and it was an upward opening parabola that you can see here on the screen. Now, that's not exactly what the curve will look like, but it gives us a good idea of its general behavior as it goes through those 3 points. Now, before we get to the end, we should get a little more information, and this is where the test points come in. And as I said at the beginning of the video, a computer or a calculator will calculate thousands of test points. It won't distinguish between the useful ones and the non-useful ones. It will just find them all. And we'd like to save ourselves some time here. So what I've done in this case is I've chosen 4 x-coordinates, and I've interspersed them among these key points that we already have. So you can see in the table on the left, the first one is an x value of -4. Well, that's to the left of all 3 of the zeros. The next one I pick is -1. That's in between the first and the second zeros. And then I pick 2. That's in between the second and the third of the zeros. And then I pick 5, which is on the right of all of them. And in the table, I've computed the y-coordinates already. So let's just see where those appear on the graph. I've got these 4 points in addition to the 3 key points. I also know how the curve behaves as it goes through the key points on the x-axis. And so finally, all I need to think about before sketching the graph is what the end behavior might be. And we did that already as well. In fact, it was the first thing we did. So if we look at the end behavior of this function, we found that it was falling to both the left and the right direction. So this tells us how to sketch the curve, and there's really not a lot of guesswork left. We have 3 key points. We chose 4 test points that are interspersed among the key points, and we know the end behavior, and we know the 0 behavior. So at this point, you can see that if you connect the dots and you generally follow the lines and the curves that are already on the screen, you can fit it together to get a nice polynomial curve. Now I'll switch off our additional lines in zero behavior, so it's a bit more clean. But you can see that it came down to having those 7 points and knowing how to connect the dots with a nice, smooth polynomial curve. Now we're going to try really the same thing with a different type of function. So we're looking at a rational function here. I've written it in both forms. So you can see a ratio of polynomials. That's our definition for a rational function. So in this case, it's 3x squared minus 27 over x squared minus 6x plus 5. I've also factored the numerator and denominator, so we have both of those on the far right. So there's 2 factors on top, x minus 3 and x plus 3, with a constant of 3 in front, and then 2 factors on the bottom, x minus 1 and x minus 5. Just like with a polynomial function, knowing how these things factor give us a lot of information that we can use to analyze the graph of the function. And what I like here about rational functions is that a lot of the techniques that we know about polynomial functions carry over almost the same way as before. In this case, let's start with the vertical asymptote behavior of the function. Unlike polynomials, rational functions can have vertical asymptotes. We're specifically looking for cases when the denominator is equal to 0. So if you're dividing by 0, we know that's a problem mathematically. We can't do it. That will give us some sort of vertical asymptote behavior in this function. So to determine that behavior, let's figure out when those points are, when the denominator is 0. And then once we know them, for each one we can pull out a reciprocal factor, and then we'll plug x into the rest of the function. And that will work almost exactly the same as it did with polynomials, except we might have a reciprocal function in front instead of a power function. Now I've set up the very first one. We can see that if x is equal to 1, our first factor in the denominator is 0, so we would have a vertical asymptote at that point. So going through the steps, we found when the denominator is 0. Let's take out that reciprocal factor. And in this case, it's the x minus 1. So I'll have 1 over x minus 1. And then I'm going to plug the value of x into the rest of it. I'll put the rest of it into square brackets in factored form. So I have the same factors on top. And then on the bottom, I've removed the x minus 1 factor, so only the x minus 5 remains. And you can see it looks a lot like the example we'd just done. We have a factor in front, this time a reciprocal, and then in square brackets, I've put the rest of the function. And what we'll do next is take this expression in the square brackets and substitute in x equal 1. And the math is a little more involved here. You can always go to a calculator to check your work on the arithmetic. But let's write it out on the board directly. So as I do this, in square brackets, I have a 3 on top. The x minus 3 factor becomes 1 minus 3, so that's a negative 2. X plus 3 factor, that is just 4. So you can see on top I have 3 times negative 2 times 4. And then on the bottom I have 1 minus 5, which is negative 4. So plugging it into the factored form gives us this jumble of numbers. But notice a few things. The 4's will cancel away. And there's a negative on the top and bottom. Those will also cancel away. So all that's left here is the 3 and the 2. So what we get out of it is the reciprocal factor, 1 over x minus 1 times 6. Now, it's obviously not a power function in the way we saw with polynomials, but we can still graph it. It's a reciprocal function. It'll have a denominator of 0 when x is 0. So if we do a quick sketch over here on the right, we take this point when x is 1, We know that's the vertical asymptote for this reciprocal function. And we multiplied by a positive number. It didn't change the orientation. It didn't flip it over the x-axis. So we know this looks really the same as a reciprocal function. It might be stretched out a bit, but we're looking at a function with two branches and a vertical asymptote at 1. So what this tells us is the rational function we're looking at, f of x, will behave like this function that we found. So we had 6 times the reciprocal factor of 1 over x minus 1. And it'll behave that way as long as you're near the asymptote, x equal 1. And more specifically, what that tells us is that f of x, this rational function we're interested in, has a vertical asymptote where as we approach it from the left side, it's headed down. So we would say here it's falling as it approaches from the left. And then on the right side, as you move leftward, you're approaching that asymptote from the right, it would rise. So we have a falling behavior to the left of the asymptote and a rising behavior on the right of it. For our other vertical asymptote, you might have noticed the other factor sitting here in the denominator. It's x minus 5. And that means that we'll have a vertical asymptote at x equal 5. I'd like you to try the same thing I just did with x equal 1. So to recap briefly, with x equal 1, we did our steps. We found when the denominator was 0, we pulled that factor out. We plugged the value of x equal 1 into the rest of it. And we got this y equals 6 times the reciprocal factor of 1 over x minus 1. And that told us about the asymptote behavior. So what I'd like you to do here, now that you can see the factored form, try plugging in the value of x equal 5. You will get a reciprocal function. And think about how that is going to determine the behavior near the asymptote. Now we'll consider the potential horizontal asymptote and or end behavior of this function. And you should think of this as being very similar to the end behavior for a polynomial function with some extra twists and turns. So for rational functions, we'll use what's called the leading term rule. So the leading term of a polynomial is just the one with the highest power of x, and that does include the coefficient. So in this problem, for example, your leading terms are the 3x squared on top in that numerator, and then the x squared from the denominator. And of course, that could be different for lots of different rational functions, and comparing those leading terms is really what's important here. So how does this rule work? Well, there's 3 things that can happen. You could have a higher power of x on top, and what that tells us is that there is no horizontal asymptote. We can look at those leading terms on their own and cancel them away. You'll have powers of x that are left over. You'll have a power function. And in that case, once you have a power function, you can use what you know about polynomials, and that will tell you if we're rising or falling as we go off to the right or the left of the graph. So in those cases, think of it like a polynomial, and you'll get the information you need. The second thing that could happen is the 2 powers are the same, and that's what happens in this particular example. We have the x squared on both the top and the bottom. Well, in that case, we only need to consider the coefficients. You can think of those powers of x as canceling each other out exactly. And then you do have a horizontal asymptote. It's the ratio of those 2 coefficients. And then the third thing that could happen is you have a higher power of x on the bottom. And in that case, we know that the horizontal asymptote, regardless, will be 0. So if you do have a higher power of x on the bottom, just know that horizontal asymptote is always 0 in that case. So as we saw, the second of the 3 cases is the one that applies here. We have powers of x that are the same. So we could think of it this way. We have a 3x squared over an x squared. The coefficients on those are 3 and 1. You can imagine a 1x squared being our factor in the bottom. And if we imagine those powers of x canceling away, we have a 3 over 1. And of course, 3 over 1 is 3. And so you have a horizontal asymptote at the line y equal to 3. Before we get to the graph of the function itself, we need to do one more thing. And I call this find some key points. So a key point is just an important point in two-dimensional space. It's a point on the graph of the function. And there's a couple that we would like to know before we get going. So the first thing we should ask ourselves is, does this function ever equal its horizontal asymptote? So we'll do the math for that in a moment, but remember that horizontal asymptote is a horizontal line that describes the end behavior of the function. And that doesn't mean it couldn't cross that line somewhere in between. So if there's this crossing point somewhere in between, we'd like to know about it. And then the other thing, as we've done for other functions, we're interested in the x and the y-intercepts. So does this function intersect the x-axis or the y-axis? Let's find those points too. And we'll throw all of those together. We'll get a set of points in two-dimensional space in the plane that we can use when we start sketching the function. So let's consider the first one. Does this function ever equal its horizontal asymptote? And from what we did a moment ago, we know the horizontal asymptote is when y equals 3. So we'll set them equal to each other. We've got our function here. I'll use the non-factored form. So we have our 3x squared minus 27 on the numerator. And then for denominator, x squared minus 6x plus 5. And we want to know if that's equal to 3. I'll use it as a ratio. So you might remember when I found the horizontal asymptote, I was thinking of it as 3 over 1. It's always good to write it as a fraction. And what we have then is a fraction equal to another fraction. And in this case, what we do to solve fractions equal to other fractions is we cross multiply. So take the numerator from one side times the denominator from the other. So I have my 3x squared minus 27 times 1, so that is the same. And then the denominator I'll multiply by 3. And I'll take each term times 3. So I'll have a 3x squared now, minus an 18x. And then the 5 times 3 gives me the plus 15. And the point of all this is once we've cross-multiplied, those leading terms should be the same. You have a 3x squared and a 3x squared. Those cancel away. So now there's only an x in one of the terms. There's no power of it. There's no power other than just x itself. So we should be able to solve for x pretty quickly. And I'll bring the 18x over to the other side. I'll take the 27 plus the 15. And in that case, we get 42. And we can see here if 18x is equal to 42, divide by 18. We get a nice fraction, and here's where I need to check what I've written here. We should get a 7 over 3. So what that tells us is when x is equal to 7/3, the function does cross over the horizontal asymptote. It'll have a y-coordinate of 3. Okay, so looking at how the math worked out, we had a quadratic equation, 3x squared minus 27 equal to 0. We solve for x. In this case, you can do it directly. So move the 27 over, divide by 3, take the square root. In this case, we get x equal to -3 and 3. If you compare that to the factored form with x minus 3 times the factor x plus 3, you could get it that way too. The point of it all is that we get 2 x-intercepts, which gives us 2 more key points. So we have a -3, 0, and then a +3, 0. So we're up to 3 key points in two-dimensional space. And we can finish that off with the y-intercept. That one's a bit easier to calculate. We take x to be 0 in this function. All that's left is the -27 on top and the +5 on the bottom. Everything with x in it is gone. And that number happens to be negative 5.4. So that gives us our fourth key point. We have 0, negative 5.4. Now that we have all the information for our rational function, let's look at how to begin sketching a graph. Just like with the polynomial function, there were some key points that we needed to consider. We had 4 of them. They're shown in the table on the lower left. So if x was negative 3 or positive 3, the y-coordinate is 0. Those were the x-intercepts. For the y-intercept, we found that if x was 0, y was negative 5.4. And then we also found a point where the function crosses the horizontal asymptote. And that was at 3. We found the x-coordinate needed to be 7/3. You can see all 4 of those points in the graph over on the right. And in addition to that, I have 3 key asymptotes. It's part of the key information. They're not points, but they are lines that affect where this graph can be and how it's displayed. So we have our horizontal asymptote at y equal 3. And we also know we have 2 vertical asymptotes at 1 and 5. Now, this is our starting point for the curve. You can see there's a lot that we don't know quite yet. Let's incorporate one thing that we did on the board, which is the asymptote behavior, specifically the vertical asymptote behavior. You might remember that there were 2 functions that came out of that process. This was the same procedure as we did for polynomial functions. And what we did was we factored out the reciprocal factor for each one out of our denominator, and then substituted in the corresponding x value into the rest of it. So we got 6 times 1 over x minus 1, and we also got 12 times 1 over x minus 5. And those are both reciprocal functions. We had sketches on the board for them. I'll show you what that might look like here. And we saw that for each of these vertical asymptotes, the function would fall as we came in from the left side of it, and it would rise as we come in from the right side. So you can see 2 branches for each of those asymptotes. And those don't exactly match the function, but it does tell us what direction we're headed as we come in toward that asymptote. And it gives us a good idea of how to connect the dots in this graph. You might be tempted to connect the dots right away. At least in that middle portion between x equal 1 and 5, we can see there's 2 points already shown, and we know how to connect those toward the asymptote. But on the right-hand side, so for x greater than 5, we don't really know a whole lot about where this curve is moving. So to be safe, let's pick a few other test points. You can see in the table on the left, I've chosen an x value of 4. I'd like to know what's happening as I move toward that asymptote at x equal 5 from the left side. And then I've also chosen x equal to 7, so I have an idea of what's happening to the curve as I move off to the right edge. So going through all of that, the 2 test points now illuminate what really should be happening here. So we can see in the middle there will be a downward moving curve connecting the 2 asymptotes. On the left portion, we can see as we move left from x equal 1, the curve will be rising. We also know there's a horizontal asymptote, so it will rise toward that asymptote at y equal 3. And then in the right-hand portion, when x is greater than 5, we see the function falling to the right toward its horizontal asymptote at x equal 3. So finally, we can sketch the graph. We connect our dots. We make sure the asymptote behavior matches what we determined ahead of time. And we can see exactly what I described is indeed what the graph looks like. So in the left-hand portion, when x is less than 1, we have a curve that approaches the horizontal asymptote from below. So it's approaching y equal 3 as we go off to the left. And it moves downward to minus infinity as it approaches the asymptote at x equal 1 from the left. The middle portion between x equal 1 and x equal 5 is that downward moving curve. So it starts at infinity at the vertical asymptote and moves down, crossing the x-axis at 3 continuing downward to minus infinity as we move over to x equal 5. And then finally, that right-hand branch, when x is greater than 5, we come down from infinity, moving in a falling fashion toward the right and approaching y equal 3 as our horizontal asymptote. Let's recap everything we've done here. Mainly for polynomial functions, we saw how the zero behavior of the function can be determined by pulling out the factor and then plugging the value of x into the remaining portion. And that tells us a lot about not just where the zeros are, but what that behavior happens to be. And then secondly, with rational functions, we did much the same thing for vertical asymptotes. So if we pull out the reciprocal factor corresponding to a vertical asymptote, we can plug the value of x into the rest of it. That will tell us something about the behavior of the function near that vertical asymptote. And then taking all of that together, we saw that having a handful of key points and potentially asymptotes, along with a couple of smartly chosen test points, can tell you a lot about the graph of a function. So what we don't need to do is pick thousands of points like our calculator does. We may need only pick 6, maybe 7 points before we understand what the shape of the graph should be. As you think ahead to other topics, let me stress how important this key information and test point method really is. Often having a graph is helpful, but also very important is knowing where to look. And by having key information and by choosing some test points, we were able to narrow our focus in a way that just a calculator wouldn't have told us. Thanks for watching.